Okay, so tell me when you've started recording.
Oh, I'm starting.
Thank you, Melvin. Thank you, Tim. Thank you, everyone. So today, intention is to present a brief tutorial, in no ways complete, about an important aspect of our computational mechanistic modeling called boundary conditions. As we heard in the introductions, my name is Sanjay Kapche, and nominally I care for our computational medicine laboratory. This tutorial will run in two parts, each of around about 45 minutes to an hour. To start, I would like to thank everyone's support. Not mentioned here is the Department of Medical Physics. Not mentioned here is also the Kidney Clinical Research Unit in Lawson Institute, led by Prof. McIntyre. And not mentioned here is the wider Western University. But other sort of agencies that we get support from are listed over here. Now, an overview of what is to happen today is that we will discuss something called differential equations that govern the physics of either blood flow in blood vessels or electrical waves, especially in cardiac tissue. As Randa was saying, we are also concerned with electrical waves in cardiac tissue, in addition to blood flow in blood vessels. This tutorial, as I said, is in no way complete, but is meant to encourage, especially our fourth years and our master students, a thorough literature search. Practice solving your problems till you are exceedingly comfortable with the knowledge that you get from problem solving. And as a culmination of your understanding, you should also try to program some accessible models. Okay, and in the first part, I will gloss over some of the relevant boundary conditions, and as examples, I will also try to do some simple exercises, very simple exercises. And in part two, I might try to focus on the actual models that we're using. And playing on my mind these days, as Namashi said, are more like the one-dimensional fluid dynamic models. Throughout, I would like to introduce biophysical principles. A couple of places you might come across the policies and standards that we have on our computational modeling. And overall, throughout these slides, in the first and second parts, is content for all theses, fourth years and for masters. And so that's the overview. And before we start, a few housekeeping rules are that both of these parts are recorded as two separate videos because we may not be able to handle one large video. One or more co-hosts may exit to convert their videos. Everyone should feel free to interrupt me, raise their hands, or write their questions or comments in the chat at any time in either parts. And so as a word of warning, my PC is marginally temperamental and it switches networks. And so if my PC loses a connection, please bear with me. I will sort of get back on track as soon as I can physically. And so the purpose of this tutorial is for general engagement. As we just saw in the introductions, we have at least 3 departments across the university and Lawson involved over here. And so in this interdisciplinary environment, I'm looking for general engagement with a focus on a specific part of the modeling, that is boundary conditions, but it is also material for our fourth year as well as Nemashi's thesis. Okay, and so the expectation is that everyone should use these slides and then some to construct content for their fourth year thesis, about 5 pages apiece. The computer science thesis should focus on the algorithms and the data processing, the visualization methods, the post-processing, and that could easily fill in a very succinct 5 pages of descriptions on how things go. And then in the master's thesis, Never mind that I'm looking for a few pages worth of material. I'm looking for some depth in the two master's thesis of medical biophysics that we are in the process of generating. And so that would be the purpose of today's exercise, and we can continue this discussion for however long in the near and far out future as is necessary. So that is the purpose of today's presentation. So I thought this is a rather sort of nice way of providing a reason for why we do computational modeling, why we even study blood flow, never mind computational modeling. And hopefully a video will come up in a minute where we have a echocardiogram, and you are to focus on this little piece over here, which breaks off and goes away into the large vessels, potentially to go and get stuck somewhere in the carotid arteries in the brain somewhere, giving rise to stroke and all kinds of horrible conditions. And so because of all of this multi-physics biology going on in all our organs, we firstly need to understand how things work. And if we then understand how things work, we then may be able to control things that go wrong. Okay, so the motivation is to understand how the biology works, especially in cardiac electrical waves and in blood flow dynamics. And if at all we manage to understand a little piece of how things work, then we may have a chance to control it. Control it means provide medication and treatment. So I thought that was a sort of very graphic video that might impress the purpose of why we are doing what we do. Now, as a very sort of extreme summary of today's discussion, and I do mean discussion, is about a certain piece of the physics description of either blood flow or electrical waves called boundary conditions. And so the text may be summarized as, if we decide to describe a biophysical phenomena, say, for example, blood flowing through the aorta, the streamlines of blood flowing through the aorta, which may be described by such a sort of symbolic object, lambda of state variables u, parameters p, to be nothing. And this could be a algebraic description, but in most cases, it will be a differential equation description. And this is a description that is provided for inside of the regions of interest. Typically, regions of interest are called omega. Now, when we are about to solve these differential equations given by the operator lambda, we must have an entity that goes with these differential equations called the boundary conditions. And I choose to represent a summary of boundary conditions with a function called gamma. This is a Greek symbol gamma. And that is a formula of state variables. I choose to call state variables using u, or derivatives of state variables. So quite often it's not enough just to assign boundary conditions with state variables, but we must assign boundary conditions using derivatives and other combinations of state variables. And boundary conditions are generally applied at the boundaries of the region of interest. Boundaries of region of interest are often written using this symbol partial d. It's also called just partial d. Fine, I want to use different words. So partial d of omega often represents the boundary of a region of interest. Now, if anyone wishes to further investigate how the physics of blood flow works, our own Meyer Zamir has written a massive book back in 2005, and that is still exceedingly relevant. And if, say, by some small chance you get through Meyer Zamir's book, there is also a book by Pinsky, which he wrote even before. which describes blood flow in the context of the brain. And so these are recommended books for practice, for exercises, and for understanding how especially these boundary conditions work. Now, here's a few definitions before we move on. The definitions come up for state variables. So variables, whenever we speak about variables, we are basically speaking about state variables, quantities that change over space and time, quantities on which you describe your physics upon. And we have then also modeling parameters. Modeling parameters typically are constant throughout our simulations. So to summarize, written in purple, we can sort of summarize our approach in that whenever there is a biological phenomena, either blood flow or electrical waves, we use the known mechanisms. We summarize these known mechanisms into differential equations, either ordinary or partial differential equations. Yeah, and these differential equations, when solved, will describe the process. For example, the velocity of blood over space and time. For example, the distribution of an arrhythmia in Randa's 3D heart. For example, the distribution of oxygen in 2D and 3D spaces, as described by Dr. Goldman's equation. In these differential equations, either ordinary or partial, we have three kinds of entities as written in brown towards the bottom of the slide. Firstly, we have independent variables. Independent variables means we have no control over these variables. These are just variables that inside of which we exist. The physical space, the 3D space, X, Y, Z, and time. Now, whereas biology and real-world applications may only have so many independent variables, generalizations do not have to stop at 4 independent variables. We can go to as many independent variables as we need to. In contrast to independent variables, model parameters, I choose to represent them by P, a vector P, are constant throughout your simulations. So if you are simulating blood flow through the aorta, then there will be a set of numbers that are constant throughout your simulation, and those are called model parameters. Generally, model parameters are estimated using experimental data. And experimental data also is used to validate our model outputs and comparing them to the third entity called the state variables. Now, these state variables are the dependent variables. These are the variables that change with space and time. They are the solutions of your differential equations, either ordinary or partial. And boundary conditions, as we saw in the previous slide, are often specified, in fact, motivated by biological and clinical observations. By the ambient conditions during the experiment. Boundary conditions are inspired by the biological/clinical motivations and are applied to these state variables. So we have 3 kinds of entities in differential equations. One is independent variables, the other one is model parameters, and the third is the state variables. For those who are interested, your differential operators will operate always upon these state variables. Now, in terms of books, I found that David Christini has written an exceedingly elegant book, which is available through our Western library that describes how to model cardiac electrical waves. So Marsden, Krog Marsden and David Christini have described electrical activity in the heart and how to simulate it elegantly in a available book. The sort of blood flow is best described by a man in Milan called Quattartoni, and this book also, I believe, is available through our Western library, which describes how to model blood flow in the human cardiovascular system. So this is at the bottom of this slide is a reading list, which is strongly suggested, at least the first few pages, or all pages. But fine, before we start with boundary conditions, if anyone at all is curious as to how model parameters are estimated using experimental data, then this is a tutorial that we created a couple of days ago, and it has decided not to work. So this is a tutorial created by Amir and Abdus, which demonstrates how to estimate model parameters using specific experimental data. The QR code on the right-hand side may take you to the relevant YouTube video. So this is a brief explanation on how to use experimental data to estimate model parameters, and in that way justify how your model behaves, somewhat justify. But fine, so okay, so the video does work, and we are supposed to see minute 34. And so take a look at that, the glyphs there, the purple glyphs there. At the top are 3 pictures, me, Amir, and Abdus, and these two are right now busily studying Timothy syndrome and hypertension, either in cardiomyocytes or smooth muscle cells. And the work has come to a place where we are looking to fit experimental data, as shown by the circular glyphs, into mathematical functions, in this case, sigmoids of activation and inactivation of ion channels. And in that way, we are estimating model parameters. But fine. So that was about estimating model parameters. Coming back to the discussion that we are having today about boundary conditions. So a boundary condition, in words, is simply a condition that a state variable or all state variables must satisfy at the boundary of a given space. So for example, if this pink region, say, is the inside of your aorta, then it may be that there are certain equations called Navier-Stokes equations or some other equations that describe how the blood flows in this pink region. But as you know, the aorta and most other objects of real interest always have a boundary. And the boundary in this case is shown by this thick black line that encloses your region of interest. Conditions must be given at this thick black line, and those conditions are called boundary conditions. These boundary conditions are the ones that totally sort of govern how your solution comes out. Without boundary conditions, you just cannot get a solution there. Now, fine. So that's a straightforward description of what boundary conditions are. So given a certain set of physics inside a region of interest, we must have conditions at the edges of the region of interest for the solution in the region of interest to exist. Boundary conditions. Now, spending a little bit more time on this, adding some graphics here. I've written at the top right-hand side, as indicated by my laser pointer, I've again written my symbolic way of writing the differential equation, either ordinary or partial. And so given this physics here, lambda of u, to be some value, I choose 0, it doesn't have to be 0. If we have such physics given, then the boundary conditions in this slide must be applied at this dark orange line that encloses your space of interest. And now this slide, the purpose of this slide is to illustrate a few often used boundary conditions, and we will practice the use of at least one or two of these boundary conditions today. And the four boundary conditions that are often encountered, firstly, are Dirichlet boundary conditions shown on the left-hand side of the slide. And Dirichlet boundary conditions are essentially conditions that provide the value of the state variables on the boundary. So you, the state variable, you could be just one number, or it could be a vector of numbers. It could be a series of numbers. So you could have voltage, calcium, sodium, potassium, all in a vector, and their values then are given on this dark orange line, Dirichlet boundary conditions. The other slightly more horrible boundary conditions say that there may not be an exchange of mass, there may not be an exchange of energy in general. And those boundary conditions, given by this sort of Einstein-looking guy, whose name was Neumann, are called Neumann boundary conditions. Neumann boundary conditions, as opposed to Dirichlet boundary conditions, involve a derivative of the state variable, as represented by this upside-down triangle working on you. We will see in a minute what this upside-down triangle means, or what it could mean, not completely. So what this upside down triangle del of u means is that take the derivative of your state variables, and never mind that, but take the normal component of that derivative. This n dot means that. So go to any location, look for the outward going perpendicular direction, and in that direction, this derivative must be some predefined value, okay? And those are your Neumann boundary conditions. Often, when your heart is being experimented upon outside of the body, say, for example, in a dish or hanging off of a lampstand or something, you will apply Neumann boundary conditions. In case your liquid must be left inside of a aorta or a coronary, we will have a variant of Neumann boundary conditions there. Now, going deeper, you can combine the Dirichlet boundary conditions, that is, take values of your state variables at the boundaries, and you can combine that with Neumann conditions, take the derivative of your state variables along the boundary, and a combination of those two, represented by this plus sign here, a combination of those two with some parameters A and B over there, are called Robin boundary conditions. So Robin boundary conditions have both the value of the state variable and the value of the derivative, or rather a combination of the two, being prescribed at the boundary. Okay, those are your Robin boundary conditions. Quite often, Robin boundary conditions come up well, they come up everywhere. I hesitate to sort of come up with a extemporary example. And the final and most horrible boundary conditions are given by this guy called Cauchy. And what Cauchy says is that never mind a combination of your state variables and your derivatives giving you a boundary conditions. Cauchy boundary conditions are basically take one boundary condition for your state variable and one boundary condition for your derivative, Neumann boundary condition, as separate equations, as separate conditions, and together they constitute Cauchy boundary conditions. So people, these are four types of boundary conditions that we may come across more often than not. Okay. Now, fine. So how do these boundary conditions, where do these boundary condition things fit in our world? Might be a question. Where is the physics? Where is the applied maths? And where's the computer science? And so if we say start at the top right-hand corner of the slide, we are interested, say, for example, in some specific biological phenomena. In quite a few of our cases, it is the flow of blood in certain tubes. Yeah. And to be able to do this computationally, as we saw in previous slides, we have to make a mechanistic biophysical model. that summarizes the biology. In case of blood flow, it is summarized by the Navier-Stokes equations. In case of cardiac electrophysiology, it's something called the monodomain reaction diffusion equation. But fine. As soon as you have formulated your biophysical model and summarized it in terms of the relevant maths, you are then ready to describe the biology quantitatively, but not before you assign a whole bunch of relevant boundary conditions as shown in the pink box at the bottom of the slide. And so the model must be told at least two things. The first thing that the model must be told is where to start from. What are the conditions? What are the prevalent conditions when your experiment started, when your simulation started, when your observation started, never mind simulation or experiment, but at what place of state variable values did your observation start? So that is an important part. And in addition to that information, we also must know in what environment are we doing our experiment. As I said, hearts are often observed optically mapped outside of the torso. Okay, blood vessels may also be studied outside of the torso. So the environment outside of the body is definitely different from inside of the body. In yet different worlds, we might take a aorta and put it inside of an artificial body. And there, the boundary conditions are yet somewhere else. In general, when simulating electrical waves in the heart, we must have either Neumann or Dirichlet boundary conditions, depending on whether you are inside or outside of the torso. And a similar argument applies for blood flow problems. But definition of the model physics, together with the boundary conditions, definitely comes before you go and obtain numerical solutions from any software. Okay. So Dr. Goldman and myself, we like finite differences quite a lot. Structured grids is what we like a lot. But recently we have started using a spectrum of platforms that are based on finite elements, on backward difference formulae. In the near future, we might even go and do spectral methods and finite volume methods. And as soon as you have your numerical solutions, using your robust or not so robust simulation platforms, scientific platforms, you then go and extract meaningful results using a process called post-processing. However, I must stress that the formulation of the problem and application of boundary conditions comes much before you go into the numerics of things, okay? And therefore, we are not allowed to think about either the physics and definitely not the boundary conditions in terms of the numerics, in terms of the software, okay? And so this is approximately how a computational studies flow might go. With boundary conditions fitting in right in the middle. But fine, a little bit of notation and jargon. In our world, there are two kinds of differential equations. One is called ordinary and the other one is called partial. And ordinary differential equations are explained somewhat in the yellow box at the top, where if you have just the one independent variable, in this case, I've taken Z to be the independent variable, then that becomes an ordinary differential equation. In case we're trying to describe smooth muscle cells today, in case we're trying to describe mouse cardiomyocytes today, those are classed as ordinary differential equations. On the other hand, if we have multiple independent variables, say for example, we have X, Y, Z, and God forbid, if we have time as well, then we must use the partial D, which means take the derivative of your state variable, yeah, while all other variables in that small increment are kept a constant. I apologize that this may be a little bit too much, but that's this has to be appreciated before you can get into even using your scientific platforms most efficiently. And just to put a picture in everyone's minds, written at the bottom is that upside down triangle. This is how you might take the gradient of any quantity in space. Okay, so you've got I, J, K as unit vectors, and corresponding to each unit vector, there is a derivative in the respective direction. Yep. And if you apply this, something called an operator, to any state variable, we get how that state variable might change with respect in space. So that would be the definition of del or nabla, upside down triangle. Coming to sort of more, how can I say it, pictorial description of boundary conditions, we may be concerned with biological phenomena as shown in panel A on the left-hand side of blood flow through the aorta. Now, this color coding is for streamlines of particles that might flow through the aorta. While we do this computationally, there are others who might have experimental kit that does exactly the same. Okay, and so in case we're interested in describing the blood flow velocity profiles, we must have boundary conditions at the inlet as well as at the outlet, as shown by these two circles, one red and one gray. Okay, unless the boundary conditions are described at these two locations, we may not be able to solve the physics, and the physics is described in panel B over here. The 3D physics here is described using the compressible Newtonian liquids Navier-Stokes equations, where we have a description of various kinds of forces being balanced. So this row here is essentially a balance of forces, of different kinds of forces. For example, here, the first term after the equal to sign is the force term due to the pressure. This last term here is a forcing term that, say, for example, an assist device might apply. Okay, and so this Navier-Stokes equation is essentially a conservation of momentum, a balancing of forces equation. On its own, it cannot describe how blood flows, and it must be coupled with something that we may find obvious, but we should never take for granted. That is the conservation of mass, the continuity equation. What comes in must go out, okay? And so in these equations, U is a three-dimensional vector that describes the blood flow velocity. So if you go to some location, it may be a vector pointing in some direction with a X, Y, and Z component. No. And pressure, on the other hand, is a scalar, but it is definitely allowed to change with time. And U and P together in these equations might form your state variables. On the other hand, written in magenta are this model's parameters. Now, rho and mu, unless sort of we are looking to make things really messy, should be kept constant throughout your simulation, either steady state or transit. Yeah. Now, most importantly, even if you have all of this gray box over here, some information has to be applied at this red circle, and some information has to be applied at this gray circle. Now, I propose, as a policy, that we have velocity profiles at the inlet, and we might discuss one or two ways in which we can come up with velocity profiles at the inlet. So I propose that we have velocity profiles at the inlet. If Nicole was sort of here, she might have described to us what this vector function f looks like. She might also use the word Wormsley sometimes at the inlet here. So my choice is to apply velocity profile. You can apply pressure profiles. That's fine with me. That's acceptable. You can have all kinds of boundary conditions, but as a choice, I would like we are going to adopt velocity profiles as inlet boundary conditions, and as outlet boundary conditions. As soon as your outlet is far away from the inlet, As soon as it is far away from the inlet, you may be able to get away, you might get away by assuming that this is a very low pressure and therefore a very constant pressure in comparison to the activity going on at the inlet. You can see already from the velocity profiles that there's a lot going on at the start of the aortic root as opposed to what's going on at the outlet. And so I propose that in our simulations, we use pressure outlet boundary conditions. Truth be told, pressure at the outlet can also be a time varying function G. Okay. And so these are some of the boundary conditions that we might be thinking about in 3 dimensions. So the point of all of this is that these are your iconal Navier-Stokes equations. It must go with a continuity equation, and these two must go with appropriate boundary conditions, consistent boundary conditions. We cannot be applying arbitrary boundary conditions here. Okay. Now, fine. Quite a few of our projects, Anki's, Nicole's, and mine, we are concerned with 1D models, Nemashi's whole rat arterial structure, are 1D Navier-Stokes. Now, I'll be honest here, this approximation of Navier-Stokes is not really what I'm talking about here, but I'll let it be. And 1D models are basically tubes joined end to end, and the Navier-Stokes and continuity equations are valid in each of these tubes. So you may appreciate that when 2 tubes come together, there's still some boundary conditions there. I wonder what they might be. But at the 2 ends, yeah, supposing blood is going from the left-hand side and coming out of the right-hand side, we might apply our favored blood flow velocity boundary condition at the inlet and pressure boundary condition at the outlet. But at the junctions of these various tubes, you must go 1 step deeper and apply a conservation. That is, as much blood comes in, that much blood has to go out. At bifurcations, what goes in must go out, a conservation equation. Okay. Now, in this slide, I would like to show you an example of boundary conditions applied to say a simple ordinary differential equation. And the ordinary differential equation is written as du by dt, total derivatives, du by dt is something simple, u squared. U squared, yeah, fine. So the rate of change of u is described very simply as u squared. And I choose 2 boundary conditions. The first boundary condition is that u at time t equal to 0 is 0.1, arbitrary. I just picked this. It doesn't have to be 0.1, it can be anything. So the blue boundary condition I pick is the initial value of u is 0.1. And the other boundary condition, to contrast it with the blue boundary condition, I pick the initial value of u to be 1, something significantly different from 0.1. Something significantly different from 0.1. And I solve this differential equation for you using each of these boundary conditions. And for the blue initial condition, I get the solution as shown by this blue line in the graph. For the red boundary condition, I get this other solution shown by the red line in this graph. As you might appreciate, if your physics is sensitive enough, then boundary condition, never mind even if it's insensitive, boundary conditions regulate what your solution comes out as. As you can see, the blue line is totally different from the red line. If we had time, we could have solved this ordinary differential equation and arrived at the general solution written at the bottom left-hand corner of the slide over here. But I hope that you can see that even in case of very simple physics, boundary conditions are really relevant. Otherwise, instead of having an arrhythmia, you might end up with a conclusion that any condition does not cause arrhythmia. But fine. Here's another very lucid example of boundary conditions. And here I choose to discuss something called the 1D heat equation. Okay. So I'm circling the heat equation over here. So it is the derivative of U, the time rate of change of U. Let's say U represents temperature at some location in the 1D rod. So we have a rod, and there are two ends to the rod. One end is at 0 and the other end is at capital L. And we're interested in how temperature is distributed along this rod. And so the time derivative of the temperature is given by the average of temperature in close by locations. And that is the physics of how diffusion of heat might work. Okay. And so supposing again that we choose to solve this heat equation with two separate different boundary conditions in the expectation to learn how different boundary conditions might lead to different solutions, we might on one hand apply boundary conditions written in the pink box on the left as Dirichlet boundary conditions. The state variable is some function f. Yeah. So you apply some apologies. The top lines are just initial conditions, and I choose to think of initial conditions as boundary conditions as well. So in the pink box, apologies, in the pink box, 3 or 4 lines down, we choose to apply Neumann boundary conditions where the derivative of the state variable is assigned a value, a specific value. I choose 0. It does not have to be 0, okay? So at both at x equal to 0 and at x equal to L, the derivatives of both these derivatives count to 0. But fine, in the pink box, we are applying Neumann boundary conditions. In contrast, in the green box, again written in magenta, the boundary conditions I choose to apply are directly to the state variable U. And I choose 0 as simple-minded boundary conditions here, okay? So again, on the left-hand side, we have boundary conditions that are Neumann boundary conditions that involve derivatives. On the right-hand side, we have boundary conditions that involve just the state variables and no derivatives. Left-hand side Neumann, right-hand side Dirichlet. Pink Neumann, right-hand side Dirichlet. And by some magic trickery, we might come up with general Fourier series solutions as shown towards the bottom of both boxes. So for Neumann boundary conditions, we might notice that we have a superimposition of many infinitely many cosine functions. So there are many nodes. N takes integral values, yeah, but they are strictly cosine functions. There are no sine functions involved in this solution here, regardless of what f you take, what initial conditions you take. In contrast, if you apply Dirichlet boundary conditions, then because of the physics, because of the combination of the physics and of the boundary conditions, you end up with infinitely many sine functions devoid of any cosine contributions, okay? And so if you try to plot the, in addition, as you can see, there is no constant term in the green box, in a green box's solution, whereas there has to be a constant term in the pink box's solution. Okay, so there's several differences as soon as you start using different boundary conditions, and therefore the point is we have to be careful about what boundary conditions we choose, what values in the boundary conditions we choose, and so on and so forth. And so I thought the heat equation is a rather elegant way of describing, of highlighting how different boundary conditions might lead to totally different solutions. Okay. And one of the very curious boundary conditions that we have to be using by, say, Melvin across the room over here, and by Gabrielle, is that if we are faced with sort of working out certain biophysical properties of a microvascular network as shown on the left-hand side, and if I then fixate my attention on this yellow region over here, yeah, I might then be also able to construct a network as shown in panel B over here, where all the nodes shown in green or black are numbered sequentially. And through each of these connections, which we might think of as capillaries or tubes or arterioles, just tubes, we might have flow going from node number 1 to node number 2. We might have flow going from node number 3 to node number 9. Yeah. And so to be able to work out these flows, we must have boundary conditions as explained in panels C and D, specifically in panel D, in that across any one given blood vessel, we have the drop-in pressure, that is pressure at the proximal end, minus the pressure at the distal end. So pressure at the proximal end minus pressure at the distal end is equal to some massive constant that depends on viscosity, that depends on the length of the tube, that depends on the radius of the tube. The assumption is that the length of the tube is much longer than the radius of the tube, but this is a constant. And this difference, pressure proximal minus pressure distal, is a constant times the flow in said tube. So the flow going from proximal to distal. And the boundary condition is written right at the bottom over here, where at any location, boundary condition at bifurcations is written right at the bottom here. That is, at any node, what comes in must go out. And the places where you see these green circles or these red circles is what gives you a few values of these pressures. And using that, you might recursively solve for the flow. And after you get the flow, maybe you go and find oxygen distribution or whatever you want from there. So these are boundary conditions in what I choose to understand as discrete equations. Okay, so that was our example 3. So I've again repeated this here. So a specification of boundary conditions only at the inlets or the outlets is not enough. A specification of the boundary conditions at inlets and outlets is not enough, but at every bifurcation or even every node that we have in our structure, we must have conservation. And this conservation equation is applied to node number 3. This conservation equation here is applied to node number 3. So we have flow coming in from node number 2. We have flow going to node number 9, and we have flow going to node number 4. So what comes in must go out. Okay, and a very elegant description is given by Matthew Olofsson in a 1999 American Journal of Physiology paper. Yeah. And I strongly suggest that you pass through at least its introduction, its discussion, its conclusions, its references even. Yeah. So Matthew Olofsson's AJP, I thought, was quite nice in describing the boundary conditions at bifurcations. And so as one of the final slides, all of this is now programmed into the scientific platforms, mechanistic scientific platforms of either blood flow or of electrical activity that is in front of us. And so for large vessel hemodynamics, yours truly maintains a platform called SimVascular. And so it's my job to answer all your questions. Yeah. There's also a robust hemodynamics platform to support our O2 oxygen transport studies. And this is maintained and developed by Dr. Goldman. In addition, we have a couple of cardiac electrophysiology platforms. One is called VCPL, developed and maintained by yours truly and Prof. McIntyre. And we have recently adopted the very large finite element-based platform called CHASTE. This has been developed and is maintained by Computer Science in Oxford. And so the summary and messages of part 1 is that we have to have a very strong feel and understanding of boundary conditions. Yeah. Never mind to understand the maths or the physics, but just to be able to use all these platforms better and efficiently, exploit and deploy all that functionality properly. Okay. For all boundary conditions, we may be allowed to think that boundary conditions are motivated by biological and clinical observations, or at least we as lesser computational modelers, we try to mimic what's going on in the biology and in the clinical observations, okay? A word of warning, especially for those running large simulations. Just because your platform does not fall over and sort of die on any small or large computer, it does not mean your simulations are meaningful nor accurate, okay? It does not mean that. All it means is that the numerical solver is somehow finding ways to salvage what is given. So you have to pay attention. We all have to pay attention and question every button we press in any given graphical user interface, in any given in-script, in any sort of given tool of the trade. Yeah. And unless we as people have gutturally understood what's in front of our faces, there's no way we can be confident of our knowledge. So thanks for bearing with me. It's just rang 2:30. I propose that we have a 10-minute break, give all our colleagues to sort of relax a bit, have a drink of water. So I'm going to stop this presentation, and I propose that we pick up again at 15 before 3 at 2:45. 15-minute break, people, 15 minutes. Thank you.